The Perceptron training rule. It is important to learn the training process of huge neural networks. However, we need to simplify this by first understanding how a simple perceptron is trained and how its weights are updated. Only then we will be able to understand the dynamics of complicated and monstrous neural networks such as convolutional neural networks, recurrent neural networks, or multiplayer perceptron, and so on. Imagine we have a binary classification problem at hand and we want to use a perceptron to learn this task. A perceptron can produce two values, either +1 or -1, where +1 means that the input example belongs to the positive class and -1 means the input example belongs to the negative class. Obviously, as we have two classes, we would want to learn the weight vector of our perceptron in such a way that for every training example, depending on whether it belongs to positive class or negative class, the perceptron would produce the correct positive one or negative one. Note here that we define which class is positive and which class is negative. So, we are talking supervised learning here, which means that we know the true class labels for every training example in our training set. As a result, the perceptron training rule, we would initialize the weights at random and then feed the training examples into our perceptron and look at the produced output that can be either +1 or -1 or interpret as positive class or negative class. So we would want the perceptron to produce +1 for one class and -1 for the other. After observing the output for given training example, we will not modify the weights unless the produced output was wrong. For example, if we want to produce +1 for positive class and -1 for negative class, and if we feed an instance of the negative class and the perceptron returned positive one, then it means that we need to modify the parameters of our network, that is, we need to modify the weights. We will keep this process and we will keep iterating through the training set as long as necessary until the perceptron classifies all the training examples correctly. At every step of feeding a training example, when the perceptron fails to produce the correct +1 or -1, we will revise every weight, that is Wi, associated with every input, that is Xi, according to the following rule. Wi is equal to Wi plus delta Wi, where delta Wi is equal to neta into T minus O into Xi. Here the variables used are as follows. Delta Wi indicates how much should we change the value of the weight Wi. In other words, this is the amount that is added to the old value of Wi to update it. This can be positive or negative, meaning we might increase or decrease Wi. Neta, this is the learning rate or the step size. We tend to choose a small value for this. As if it is too big, we will never converge, and if it is too small, we will take forever to converge to the correct weight vector and have a decent classifier. This step size simply moderates the weight updates just so the updates would not make an aggressive change to the old values of the weights. T is the ground truth label that we have for every training example in our training set. For a classification task, as we know that our perceptron can produce either +1 or -1, then we will consider T to be +1 for positive examples and -1 for the negative examples. Then we will train our classifier to produce the correct +1 and correct -1 for the positive and negative examples. That is, +1 for positive examples and -1 for negative examples. O is the output of our model, which in this case can be either +1 or -1. Xi is the ith dimension of our input training example X, which is connected to the weight Wi. Do remember that perceptron do have a drawback. The perceptron rule finds a successful weight vector when the training examples are linearly separable. It can fail to converge if the examples are not linearly separable. Gradient descent and delta rule. A gradient measures how much the output of a function changes if you change the inputs a little bit. Gradient descent is an optimization strategy. It is used while training our model. It can be combined with every algorithm. Delta rule. The delta rule is an interesting mechanism for searching the hypothesis space. Actually, the delta rule uses one of the most popular search technique in the hypothesis space, that is called as gradient descent. Using gradient descent, the delta rule strives to find the best fitting model. The delta rule uses gradient descent as an optimization technique and tries different values for the weights in a neural network, and depending on how accurate the output of the network is, it will make certain adjustments to certain weights. That is, it increases some and decreases the other weights. It will try to increase and decrease the weights in a way that the error of the output would go either down or up during the training session. So, the delta rule uses an error function to perform gradient descent learning. To understand this situation, imagine a blindfolded man who wants to climb a hill with the fewest steps possible. He just starts climbing the hill by taking really big steps in the steepest direction, which he can do as long as he is not close to the top. As he comes further to the top, he will do smaller and smaller steps, since he doesn't want to overshoot the top. It is this process can be described mathematically using a gradient. In the figure, the red arrows shows the steps of our climber. Think of a gradient in this context as a vector that contains the direction of the steepest step the blindfolded man can go, and also how long this step should be. If the training examples are not linearly separable, the delta rule converges towards a best fit approximation to the target concept. The key idea behind the delta rule is to use gradient descent to search the hypothesis space of possible weight vectors to find the weights that best fit the training examples. To understand the training rule, consider the task of training an unthresholded perceptron, that is, a linear unit for which the output O is given by O is equal to W0 plus W1x1 plus W2x2 so on up to Wnxn. It means that O of x vector is equal to W vector multiplied by x vector. To derive a weight learning rule for linear units, specify a measure for the training error of hypothesis relative to the training examples. That is, E of W vector is equal to 1 upon 2 summation of for all the training examples belonging to the training space TD minus OD whole square, where capital D is the set of training examples, TD is the target output for training example D, OD is the output of the linear unit for training example D, and E of W vector is simply half the squared difference between the target output TD and the linear unit output OD summed over all training examples. This error function, that is E of W vector, measures the difference between the generated output and the target output for every example small d across the whole training set capital D. Note that the error is a function of our weight vector. The delta rule searches for these weight vectors and uses them to generate the output for a given training example. Then, by measuring the error, it would update the previously chosen weights to new values in a way that the output for the subsequent training examples would get closer to the ground truth. So, the more the training goes on, the better weights would be. The delta rule will find, and the error for those weights would become less and less, until eventually the network has converged and we say that the model has been trained. So we have learned that the delta rule guarantees to converge to a model that fits our data the best. The best fit might be a terrible model, but still it is the best that the delta rule has been able to come up with. We also learned that the delta rule uses gradient descent as the optimization tool to search the hypothesis space of possible weights for our artificial neural network. Visualizing the hypothesis space. We have been talking about the hypothesis space and the gradient descent algorithm used by the delta rule to search this hypothesis space of weights for the neural network. We have never actually had a glimpse into this hypothesis space. Let us consider a simple neural network and try to visualize the entire hypothesis space of weights with their corresponding error values. We would want to find the best fit model by finding the weights that would minimize the error on our training data. Let us consider a simple neural network as shown in the figure. In the figure, every input training data is two-dimensional, denoted by x1 and x2. We have a weight value to be learned for each dimension, that is W1 and W2. The weights and input values are linearly combined to constitute capital Z. Then Z that holds the pre-activation value for our linear neuron will go through a linear transformation through the neuron to produce the output capital O. Then the error will be computed, and then using gradient descent we will search for the weights, that is, by modifying the current weights that would minimize this error over the entire training set. The error function that we are going to be using is the simple yet quite popular sum squared error function as described. One common error function is E of W is equal to 1/2 summation of for all small d belonging to capital D, TD minus OD whole square, where TD is the target output for the training example small d and OD is the output of the linear unit for the training example D. Note that the error is obviously a function of input training data as well and not just the weights. We tend to consider the weights in our mathematical representation of the error function, as these weights are the ones that we could alter and tune to minimize the error, while we don't have the same control over our training data. Note that in the figure, capital D is our entire training data or training space, and the error could be explained in a more intuitive fashion as for any given set of weights, the error function measures the sum of squares of difference of the output of the model and the target output across the entire training set D. The whole thing is divided by 2. In the figure, we can see that the plotted surface of our error function for a synthetic data set across a wide range of possible weight values for our simple neural network. We can see that it clearly has a global minimum, and that minimum happens at a specific value for W0 and for W1. Any other value would correspond to higher error value on the error surface. Note that while training a neural network, we rarely have a nice behaving error surface such as the one we have considered now. It tends to wobbly with loads of local maximums and minimums. Given the way we have defined the error function for linear units, the error surface is always a parabolic with a single global minimum. Typically, before gradient descent would start to even explore the hypothesis space of possible weights for the neural network, we would have to initialize our weights to some random values. Notice point A in figure on the W0 W1 plane, which corresponds to this randomly initialized set of weights. How should we change W0 and W1 so that the error would reduce to the fastest way? What is the direction of this steepest descent in error? Gradient descent searches the hypothesis space of possible weights and finds the direction of the steepest descent in the error and tells us how much we need to change all our weights so that with our new set of weights we will have had the steepest decrease in our error from the initial old value. The result will move from point A to point B as shown in the figure. After gradient descent took one step of optimization, the new set of weights at point B will be almost 0.0 for W0 and almost a certain value for W1, maybe minus 9.0. As gradient descent would take more and more steps of finding the direction of steepest descent in the error surface, the parameters of the model keep updating and updating until we reach a global minimum. We learned that gradient descent searches the hypothesis space of the parameters, that is, the weights of the neural networks in this case, and it keeps changing the parameters in a way that we would have steepest reduction in the error at any step of optimization. Given an initial set of random values, gradient descent finds a weight vector that minimizes the error. We have to know that gradient descent is a repetitive search algorithm that at each step strives to modify the weights in the direction of the steepest descent in the error along the error surface as shown in the figure.